for the invitation. So, pleasure to be here. Great conference. Thank you so much. So, I'm speaking about this new program of algebraization. So it's like build the orthogonal to categorification. It's basically for the people who already have pain in the neck of looking higher, higher, and higher, so they can just. So I will promise to stay just with one category. Okay. So, and I'm a topologist. So the usual things we are studying in topology are the categories of the n-dimensional cobalt. So the object here are n-1 dimensional manifolds and cobordism, morphs, cobordism between them. And what I'm proposing is to study such thing, it's to replace them by equivalent categories, again, just one categories of algebraic nature, basically categories generated by just one algebraic object. Usually, and one example of such behavior, which everybody probably knows here, is the category of two-dimensional cobordism. So here the objects are just circles, so closed one-dimensional manifold, and morphism between them are orientable surfaces. So this is, for example, one. So I will always read, so I will try to be consistent to read my morphism from bottom to top. So this will be morphism from 1 to 2. Yeah, so alternatively, clearly, you can draw another morphism to go from 2 to 1. Then you can draw cap and cup. And actually, because we know how to classify surfaces, what we know is that any morphism, so if we consider this is a monoidal structure, monoidal category with monoidal structure given just by disjoint union, then actually these 5 morphisms generate the whole category in the following sense that every surface orientable closely surface just can be obtained by composing this guy and taking the disjoint union of those. And now on the algebraic, from the algebraic point of view, as clearly, so you can consider this object as 1 here, and this object comes equipped with some algebraic structure. So for example, this morphism, you can consider as a morphism from 2 copies of S1 to 1 copy of S1. And this morphism I'll call multiplication. And this morphism I'll call co-multiplication. And this I'll call co-unit. And this I'll call unit. And this is my graphical notation for the things. And this will be just and basically we are coming to the main theorem in this. So kind of pure theorem in business that 2-cop is a symmetric monoidal category really generated by Frobenius algebra object, which is S1 in this 2-cop. So who is the Frobenius algebra? So the Frobenius algebra, it's an algebra, so which consists of a vector space A, coming equipped with multiplication unit, co-multiplication, and co-unit, in such a way that this operation satisfies some obvious axioms. So for example, multiplication is associative, meaning this. Co-multiplication and co-associate, meaning just returning this upside down. Then there is some unit axiom, which looks like this. And so on. And again, so there is the upside down of this thing. And the only new axiom is a Frobenius axiom, which tells us that if I co-multiply some guy and then multiply here, then this is the same as multiply and co-multiply. And this is the same as doing a symmetric picture on the other side. So this is a Frobenius axiom.
It's commutative Frobenius.
Exactly. Commutative. Sorry, thank you. Exactly. That it's commutative, meaning that multiplication is commutative. So this is meaning.
Is it a Hopf algebra with this extra?
No. I'm coming to so just a sec, sir. I'm coming, so and thank you for Exactly. So like the aim of this talk would be to generalize this tree to the creation of n equal 3 and 4. So actually 2 we already considered, to 3 and 4. And in addition, I will also consider some category of two-dimensional CW complexes. So for this topological setting, I will establish exactly the same, that this topological category will be some monoidal category, braided monoidal, usually generated by something. And in this my setting, so in all settings, so except for this trivial example, I will need to replace the Frobenius algebra with Hopf algebra, exactly as it was proposed by Eric. Okay, and so who is a Hopf algebra? So Hopf algebra, you're right. So this is a vector space equipped with exactly the same operation. And in addition, you need also some endomorphism of H, which is invertible endomorphism, which is called antipode. Okay, so again, my graphical notation for all morphism would be exactly as a core of this here. And what is the difference is that these guys form a bialgebra. Bialgebra meaning, so clearly, so the algebra structure is just associativity and unit. Co-algebra, it's a co-associativity axioms, exactly this one and reverse. But now bialgebra, it's a little bit more. And bialgebra, it's actually this, it can be either bialgebra or Frobenius. So it's a replacement for this Frobenius axiom. So what you're doing in Frobenius, in Hopf algebra, if you would like to compute this guy, so what you're doing actually, so you're starting, so for example, you would like to compute, I don't know, if it's helps somebody, you would like to compute delta of product of x and y. So what you're doing, you first co-multiply each of them. So this is a Stiegler notation for, is it visible? So you just co-multiply x, you have these two guys, you co-multiply y, have these two guys, and then what you're doing, you're exchanging x and y, and then you multiply back. So in the pictures, it's like this. So you exchange this, and as long as you're sitting in vector spaces, you're exchanging it just flip. And so this is a new axiom which replaces the Frobenius axiom in the Frobenius setting. And otherwise, so the other axioms are the same, but this is a new input. And then you have this antipode, so you need to claim something. So in so group algebras, for an example of Hopf algebras, so you their antipode is just the inverse. Exactly. So my notation, my graphical notation for the antipode would be this is for S, and this is for S minus. Okay. And so now if I put S, co-multiply and multiply, this is the same as unit and co-unit. And this is the same as doing this the other way around. Okay, so this is a full definition of the Hopf algebra I gave you. Okay, so I will work with this object, except I will consider this Hopf algebras in some braided monoidal categories. So I'll assume that my C be a braided monoidal category. And I'm interested in a Hopf algebra object in this category. So what does it mean? So it means that this object have to come together with some structure morphism. So for example, it should be a morphism from the two copies of this guy to just one copy, satisfying associativity axiom and so on. Yeah, so it should be another one satisfying the co-associativity axiom. It should be one corresponding to unit, co-unit, antipode, and so on. And they should satisfy exactly the same relation as what I gave here. It was an example of a Hopf algebra in vector. Yeah, but now the only difference is that I'm sitting in the braided monoidal category. So for this flip, which I need here to exchange these two entries after the co-multiplication, I will use my braiding. So this is the only point where the difference of the Hopf algebra in braided monoidal category distinguished from the Hopf algebra in vector spaces. Okay, and I will be interested in such objects. So I will be interested in construction of Hopf algebras in braided monoidal categories. Okay, and so I like examples. And so perhaps you will say me, so there is no such object. Yeah, it never happens, but indeed, just the category of three-dimensional cobordism, a little bit enhanced. So I'll call it 3-cob. It's perhaps not completely the standard category. So it's a category of connected, oriented, three-dimensional cobordisms between connected and one-punctured boundaries. So what does it mean? So who are the objects of my categories? So the object here is a punctured surface. So meaning that I'll draw the surface as such a square. So this is clearly G0 surface, just a disk. And I'll just add on top of it G handles. And this object I'll call G. So this is basically I will always work with so-called pro category, meaning that always my object will be naturally identified with natural numbers. And also monoidal structure on my category will be identified with just adding of these numbers. So this is my, so I will call this object sometimes FG, so surface, so but I'll also call it just G. And now a morphism will be a three-manifold. Actually, a pair. Three-manifold is a parametrization, and it will go from FG prime. And the three-manifold will be equipped with a morphism from FG prime to the boundary of this three-manifold. And let me draw this G bar, so G prime, sorry. So this can be obtained by taking a three-dimensional cube. So because I'm drawing my morphism from the bottom to top, which I'm trying to keep here. So I'll add G handles to the bottom guy. So here it will be G handles, so this will be FG. This will be FG prime. And now this FG prime should be this inverted orientation. So it means I will draw it by this with a different color. So I'll use this. So I will remove G prime handles from the solid guy. So this blue color just means that the surface FG prime is obtained from this disk by removing the small neighborhood of these points and removing the tubular neighborhood of these attached handles. And then this is just so the boundary of this guy is called FGG prime, and every three-manifold is equipped with a parametrization, meaning diffeomorphism from boundary of this modeled from three-manifold to the boundary of my manifold. Okay, so this is my category. So composition just gluing along the boundary. Modular structure, monoidal structure is monoidal structure. So I'll draw these cubes just like this. So I'll draw it like this. In monoidal structure, it's just putting them apart. Okay. So this will be my monoidal operation. So just gluing the side, so because everything is parameterized, I just put this cube on side of the other cube. And this will give me a monoidal structure, which correspond to just adding of this number of handles on both on top and the bottom.
The boundary is supposed to be exactly just this joint union of FG and FG prime, yeah.
Exactly.
So these walls aren't really there, the sides.
I mean, it's even it's even not real disjoint union because the boundaries, the full boundary include even this, even this. Yeah. So actually, yeah. But exactly. But I would like to work with this parameterization, which allows me, which split. Actually, this is just one surface with G plus G prime handles. Yeah. But I'm splitting this using my parameterization into these two parts. So which allows me to speak about more from one to the other. Okay. So after we understood all this, then we are coming to, okay, so perhaps I should also say that two such morphisms are considered to be equivalent if there exists a morphism from M to M prime, which intertwine the parameterization. Okay. Okay, and then the fact which was observed by Ren in theta is in the 90s, and then many people worked on this, in particular, Perla and Lubashenko. So the fact is, and it's perhaps not surprising from that the object 1, or which I also call F1 in this category, is a Hopf algebra object. Braided monoidal category. Braiding, perhaps. Yeah, okay, sorry. So let me give you braiding. So who is a braiding? Braiding is a morphism from 2 to 2. Yeah, so this is 2, this is, so I should add here 2 handles, 2 blue handles. And the braiding is this guy. So this monoidal structure together with this braiding makes this 3-cop to a braided monoidal category. And I'm claiming that this just the object 1, which is in this case puncture torus, that this puncture torus is actually Hopf algebra action, Hopf algebra object. And in order to prove such a statement, what one need to do is to define the all structure morphism for this object, and then to check the axioms. And actually, so the axioms, I always giving this to students, and they have a lot of fun with this. So if you have time at some point, so to check, for example, that such a thing work, this is just 5 minutes, but it's very informative. Yeah, and here are the structure morphisms. So this is a multiplication morphism from 2 to 1 is a multiplication. This is a morphism from 1 to 2, which is a co-multiplication. This is a unit, which is a morphism from nobody, so from tensor unit 1. This is epsilon, which is morphism from 1 to nobody. And this is the endomorphism of H, which are just antipodal integers. And so this was where basically, so this was observed by Crane and Yetta. I should put names here. So Crane and Yetta observed that this guy is actually is Hopf algebra object. But then clearly the next step would be to ask, is the whole categories generated by this Hopf algebra? Yeah. And what you see that so if you don't see what is on there, so if you see it just on this 6 morphism which we need for the Hopf algebra, you see they are all embedded in R3. Yeah, and clearly you cannot embed every 3 manifold in R3. So it's impossible to obtain something non-embeddable in R3, its composition and joining together of these cubes. So clearly it's not enough. And you know, actually also what one needs to build into this algebra in order to be able to construct every 3-dimensional manifold, because we know that all 3-dimensional manifolds are obtained by surgery on links in S3. So therefore we need to build in some kind of surgery components. And this is what is this lambda, which I call integral, is going to do for us. So this red circle just means that I'm removing this circle out of this cube. I'm removing the tubular neighborhood of this guy, and I'm gluing it back with 0 surgery. So this produced for the zero surgery in this setting. So this is a co-multiplication, so in some sense dual to this guy, which so this is a morphism from 0 to 1. And there is a surgery on this removed tube. Okay, and these are just so-called ribbon morphism and ribbon inverse morphism. And all this structure comes with some relations. Yeah. And who are the relations? So first of all, we already agreed with you that we will do the exercise to check the Hopf algebra axioms. So it's just Hopf algebra. So here, Hopf algebra on this. Then the integral and co-integral satisfy the integral co-integral axioms of the Hopf algebra. So the main of them is just so I exactly actually do this validation. So the integral is a guide from 1 to nobody. So it's will be denoted by such an arrow. The co-integral will be denoted by such an arrow. So it's from nobody to 1. This guy we denote just by endomorphism, putting this one. So this is just one saying that this is one positive twist. And here we will put -1 saying that this is endomorphism of H, which is equipped with a negative twist. Okay.
How you do the surgery again? So could you please repeat how you do the surgery again? So you remove the red.
I remove the tubular neighborhood, it's just the usual. So I'm removing, so the zero surgery meaning I'm removing. So for example, this is my C. I remove, so this is an empty torus. I removed it. So this is my removed solid torus. And the zero surgery means I'm taking this disk here, which bounds because it's a solid torus, and I glue this D2 into the neighborhood of this logic. Okay.
Thanks.
So this is a zero surgery.
Can I ask a question? I don't understand these little twists that appear in S, inverse S, and V.
Okay,
Each blue thing is like a tube that I hollowed out.
exactly, but it's parameterized tube.
A parameterized tube.
Yeah.
Okay, I see. So you could just,
Exactly. This is a twist and the parameterization. Yes. Okay. Now, so I'm coming to this relations. Okay, so I can spend half an hour on these relations, but I don't want. So I just writing you, if you have never seen the integral, so integral, this is a defining relation for the integral in the Hopf algebra. That if you apply integral on the one part of a co-multiplication, then what you will get is unit here and the the integral here. This is a defining property of the integral. There's another property, so which I'll in all this business I'll use unimodularity. So if you put S here, this is the same, so it's S invariant. And the inverse of these things also works. So this is the axioms. So for the ribbon is the same as you probably know. Any ribbon category should be an central element compute with multiplication, such things. So I don't want then what you can also define using the structure which you have, and sometimes it's useful to define it. So, and I will use the symbol for it. This is so-called Hopf pairing, which can be defined by using 1, then the ribbon element here, -1, so -1 twists, and you correct this twist by +1 and +1 here. And the picture for this guy is the morphism from nobody to 2. And and the picture in terms of would be like this. And this is Hopf link. So therefore, this is a pair, co-pairing going from nobody to 2. So this is called Hopf co-pairing. But you see, it's not something additional, so it's just built using the structure we have already. But this Hopf co-pairing need to satisfy this axiom, which Hopf co-pairing usually satisfy. So it's intertwined between multiplication and co-multiplication. this is a property. And otherwise, so the two additional things which we require is that if you have integrals up into top pairing, then this is the same as a co-integral. This is this property called factorizability. And the Hopf algebra is this property called factorizable Hopf algebra. And we have normalization axiom, which I can ask or I cannot ask. This is, you can just remove each time if you have a unit multiplied with positive or negative twist and applied integral on it, then you can remove this. This is called an anomaly free Hopf algebra. Or
Is this also Crane-Yutter or
sorry.
this extra relations in Crane-Yutter or in your work, these relations?
So these are relation which I in additional require my Hopf algebra to satisfy. And I will give a name for to this Hopf algebra, so I'll call it Kerala. So Kerala Hopf algebra, it's a Hopf algebra, braided Hopf algebra and braided monoidal category, equipped with this structure. So in addition to being Hopf algebra, it has an integral, it has co-integral, it has invertible ribbon element, and if you wish, co-pairing sigma, so I can call it sigma. So and this data satisfies the axiom which I just cited. Then this is a Kerala Hopf algebra, and what Kerala, so this is why I call it Kerala and not Crane-Yutter, because Kerala was interested actually in proving the following conjecture. That this category 3 Hopf is actually equivalent to the category 3 alg. And 3 alg is just a braided monoidal category freely generated by one Hopf algebra object and by Kerala Hopf. So this was conjecture of Kerala. And this was around 0,0. And then around 0,8, Habiro came and he said, this is not true. And what is true is you need to add one additional axiom. And I draw for you this axiom. This is called braided co-commutativity. So this thing is the same as this one, where this is an adjoint action. So in the adjoint action, you know how it works. So adjoint action, I co-multiply this guy and I walked on one side. So I act on one side here, I multiply with this guy and on the other side with S. So this is adjoint action. Okay, and then was conjectured by Habiro is that if you call 3 alg a braided monoidal category, freely generated by a braided co-commutative algebra, then this conjecture is actually true. And this is what we proved actually. So we proved this together with all my collaborators. But this is indeed the case. So actually, Habiro, so he completed the Kerala axiom to the correct set of axiom. And what is surprising in the whole business is that powerful actually comes from completely different 4-dimensional setting. So what we really prove is that there is a certain category of 4-dimensional cobordism, which we called 4HB for 4-dimensional handle bodies. There is a 4-dimensional category, which is equivalent to some 4 out, which is again braided monoidal category generated by Opschutter-Galini algebra, one Hopf algebra. And from this thing, by taking boundary on the topological side and quotient on the algebraic side, you arrive immediately to this is actually corollary more or less. So after you set the whole structure of what we actually proved. And this theorem was proved by Bob Schwenker-Gallini first, so around 11. But somehow it was completely unmentioned. So at least I learned about this just from my pastor student at some point. I gave her just to read about this project, and she found that, oh, but it's all already done. Oh, wow, interesting. Okay, so and apparently so nobody believed in the proof, and it's appeared in a very not prestigious journal, and I have never, and actually so then when we first used the results and wrote something ourselves, then the referee told us, but nobody can understand the proof. So it's 230 pages, uses all methods from branch covers, coverings of all possible. So different techniques in low dimensional topology, which according to our referee, nobody knows all of them. One part was the other part, so nobody could check. And so this basically, because we kind of like to work on this because I think it's important for object in topology and also in algebra. So therefore, like end of the last year, I think, or beginning, end of the last year, I think, or beginning of, I don't know. We put a new paper on the archive, which is, and basically what we did, we honestly shortened the proof by 100 pages. But it's really honestly because we draw the whole diagram, the whole calculus, we never use anything from there. It's completely independent and it's written in more modern language so that it's, I hope it's more understandable. So at least everything what I, so just look at the preprint, and this is preprint by the 4 people there. And so there is a new proof, which is with the range Bergalini, and this is 23 if I'm not mistaken. Okay, and so let me perhaps tell you who are these actors here on the left and on the right. And then I'll take some time to explain how it's related to 3D topology and to 2D. So 4HB is a category of 4-dimensional two-handled bodies. So you can, so the objects of this category are 3-dimensional one-handled bodies. So each such thing. So now it's just drop the dimension. So it's 3-dimensional. So it's a solid. So it's a solid. And now then you take them. So this boundary is so part of the boundary times an interval. You put here another such guy. The morphism from one such guy from another such guy, you obtain in the following way that you take it times an interval, and you are in inside 4-dimensional cube like this, and then you add additional 1 and 2 handles on the front boundary, so you can have 1 and 2 handles going here. For example, can go through this handle, go it out, so here it can be noted or linked or whatever. So it's complicated pictures, and then again go through this one handle. So or just on the front boundary, you draw whatever Kirby diagram you want. And so it's difficult to draw such pictures. So therefore, what we draw are the Kirby diagrams. And the Kirby diagram would be this. So if I start just with one guy, then I will have one handle, which I denote with the dotted circle. Here, so, okay, so this is notation just for one handle. So if you will have more handles, you will copy this picture many times. You put the same picture on top. For example, let us work on top. Let us take 2 such guys. And now here in between, you can have whatever tangle, whatever Kirby diagram you want, any Kirby diagram. So any link which consists of dotted and undotted components. Dotted components are always unlinks. So nodes like this, but they can be linked with dotted components. So just any Kirby diagram can be put it in sets. So in composition, it's a tangle composition, the usual one. So this is 4HB. Now you can see that these pictures up to usual Kirby moves. And the usual Kirby move is a cancellation of the 1-2 pair, looking like this, that if you have one handle and here you have 2 handles, which can be linked or knotted or whatever, you can always remove sensitivity. This is 1-2 handle cancellation. And there is another thing when if you have two handles, you can always slide 1-2 handles over the other handle. So you can always do that. So these are the 2 moves which are the comparison. So it's just a category, just usual category of 4-dimensional 2-handle bodies. So I'm not allowing addition of 3 handles. And I'm not allowing the cancellation of 2-3 handle pairs. So I don't have 3 handles. I don't have, so this means I'm considering my handle bodies not up to diffeomorphism, but up to finer equivalence relation, which is called 2 deformation. So the equivalence relation is called 2 deformations. And these these 2 deformations are just generated by all handle slides, which does not include 3 handles. So an additional move would be that. So this is a 2 handle which bound this, and I can. So this is. So if I add the 2 deformations, this additional guy, then it would be diffeomorphism. Then I will be considering all the more. I'm not doing that. I'm stopping. So I'm just working with honest, only 4-dimensional 2-handle bodies. And can I write here?
Don't recommend it. The chalkboard's pretty bad.
Okay.
It's not really a chalkboard.
Okay. Then I'll probably go there. So let me just define you quickly who is 4HB. And 4HB so this category, the category of so this is again braided monoidal category, really generated by so-called Boccio-Pergolini Hopf algebra. So who is this guy? So it's again a Hopf algebra object in a braided monoidal category. So it satisfies everything. So it has a multiplication, co-multiplication, S unit co-unit is minus. Then I will require the whole other structure. So it will be almost like a Kerala algebra. So it will have integral, co-integral, invertible with so ribbon element. It will have a co-pairing defined in the same way using the structure we have here. And the only difference that instead of this factorizability, so I don't want factorizability anymore. And I don't want this one. So it's not, so I'm removing this braided co-commutativity. And instead of this braided co-commutativity, this basically tells me how do I transport the ribbon element through the co-multiplication. So if you have seen the formula for one, and this algebra tells you what you have to do. So I co-multiply, and I have here my co-pairing, and here -1 and -1. Yeah. So this is the guy who goes instead of the braided co-commutativity. So which I removed, and instead of factorizability, I have the following move, which tells me what is, so it's express the positive braiding through the -1. So if I take the -1, then I can do the following. Here it's also here I will need the thing. So these are the two additional axioms which I have never seen before. So I learned this from this paper of Pergolini. So these are just two new things. And if you have an algebra satisfying this axiom, then basically what you are working with is this category of four-dimensional two-handle bodies up to two deformations. So basically this optional Pergolini algebras control completely this thing. And this means also that this algebra allows you, this is a theorem which we prove together with Marco De Renci. That this allows you to classify the four-dimensional TQFT on these categories in the following way. So assume that you have such a TQFT functor, or I think TQFT it's called in this audience. I'm too old to remove that. So assume that you have such a TFT where the C is a unimodular even category. Then there always exists, basically to define now, you just need to tell me where to send this object H. Yeah. So basically you know that each time you have a TQFT, when you find this Bobchio-Pergolini algebra in this on the right hand side. And indeed, so there is your Pergolini algebra here, which is so-called end of this category. So if you don't want to, so down to earth, if you just take the representation category for quantum group, then this will be just a joint representation. So basically for every quantum group, you have a TQFT by sending the defining object of here just into the adjoint representation, and it's always give you TQFT. Now, the question is when such a TQFT is interesting. And it's interesting actually if this C is not factorizable. Because if it's factorizable, meaning basically that this Hopf pairing is invertible. So that you have, or you can find a dual one such that duality works. So if you have this, so if this is factorizable, then what we proved is that this TQT actually factorizes through the boundary. That you have a natural boundary, so perhaps already I draw these pictures in a way that if you just take a front boundary of this picture, you are back to the 3-corp which I had before. So you have a natural map, which is the boundary map from this 4HB to the 3-corp. And in the case of the factorizable category, you just see the boundary. And then here you take the Kerlachov algebra. So then exactly, so this is then 3-alg. In this 3-alg you have a Kerlachov algebra. This Kerlachov algebra is just a quotient of the 4HB, and you send it to the adjoint representation here. And this is commutative diagram. So this is basically what we proved.
On a class, so I had wanted to ask before and I didn't. I think for 3-alg, an example of a curler Hopf algebra would be the coend.
So it's
It's like-
depend how you so I mean we set it this in a way that this is adjoint, not the co-adjoint representation, but both would work. It's just kind of duality between. So exactly. So 3-alg it's a self-dual. So for 3-alg it doesn't matter whether you take adjoint or co-adjoint. This is and the duality given by this Hopf pairing, which is invertible. So it's an isomorphism.
But there could be other curler Hopf algebras besides the coend algebra.
Absolutely. Yeah. So what this theorem tells you is that each time you find one, you have a TQFT. So we found this one. We check. Yeah.
I didn't really understand this theorem. So what it's saying is that a functor from 4HB to C is just determined by a choice of a BP Hopf algebra in C. I see.
Yeah. And in particular, this functor cannot see any four-dimensional behavior in the case when the target category is a factorizable. So in particular, so this is the same as saying C is a modular category. So this, for example, answers a question which many people, so like for example, Turaev and Viro, Crane Yeta, and Justin Roberts, they define four-dimensional PQFT using modular category, modular tensor category. And basically this theorem tells you that you will never get anything interesting out of it because your functor will see just the boundary. So I'm lying here about anomalies. So if you have anomalies, you modify this a little bit, you get some, yeah.
But this theorem is the same as the theorem before HPE with before L.
So it's like they were not considering the QFT at all. So, and we just checked that, so I mean, we checked that that this adjoint representation or end or co-end satisfies this axiom. So therefore it's our, so this is, it's not a big deal, but this is what we checked.
Okay, no, I understand.
Okay. And so why these people were doing all this hard job and writing paper of about 300? Because they were interested in so-called Andrew-Curtis conjecture. This is, I hope I have another 10 minutes to tell you, this is basically the main motivation probably for this work, which is Andrew-Curtis conjecture. And here, so I will consider the category of two-dimensional CW complexes. So my CW complex will always start with just one point. And we'll have, so it's a zero cell, always one zero cell, and one cell with just n. So any object, again, object identified with natural numbers. And morphism from such a guy to another guy, it will be adding two cells to the thing. So for example, so morphism from, so such a two cell, do it here, it will be morphism from 1 to 1. And I would prefer to draw it in this way. So I will just draw it as a cylinder as we usually draw the identity morphism. And I will just put this in pink, which means that I'm collapsing this H to a point. So if I collapse this pink part to a point, what I'll get is exactly this picture. This is a morphism between two W complexes, okay? Then I let me give you another example. So for example, such a guy. Oh, no. So okay, so I have to also, so the one cell should be oriented. So this is pair of pants. Do you agree? So this guy I can draw as such a guy. This is in my locus which I so collapses to the points, and I get exactly this guy. And I would like so this category of two W complexes is actually equivalent to the category of relative group presentation. So who are the object here? So giving some alphabet with some letters, so the object will be ordered sets of letters. So for example, so I'll put here labelings A and B. So a morphism from some ordered set to another ordered set, and because it's relative, so I can have some not ordered set C, and here so relation would be some ordered sets. Letters, yeah. So this is a morphism in this group presentation. So let me just write. So this guy in this form, it would be morphism from A to B, is empty C. The relation is A, B minus 1. The relation are given by the two cells. Okay, so the second guy, so again, I need to choose letters. So the second guy would be, so from the A1, A2, this is ordered set to the B. Again, C is empty, and the relation is A1, A2, minus 1. So such things, yeah. So those CW complexes and this relative group presentation, it's the same thing. So yes, now I need to tell you who are the relations. And so the relation, clearly you have cyclic permutation of lattice in the sets. You can change the relation to the -1 of the relation if I'm just reading it rather than using the others. And then there are important relations which are cancellation of 1-2 pairs, which means that I have a cell which glued here to some collection word. I'm reading the word along the cell and put it equal to 1. Yeah. So on the level of the group presentation, it looks like A, B, C, R was replaced with A, B, C, and then additional generator which correspond to this cell. And the relation is C. This is any word multiplied with any word is equal to. Okay, so this is this cancellation of 1-2 pairs. And then sliding of 2 cell over another 2 cells, this will change relation to something like this or to this. This is just sliding of a 2 cell over another 2 cell. And the last one is pushing 1 cell over 1, pushing a 2 cell over 1 cell. Or 1 cell. And in this case, the relation changed. Oh, sorry. So this is a pushing and sliding replace RI. Okay. Okay, so these are the relation which I'll call AC relations. And if two presentation can be related by this AC relation, I'll to call them AC equivalent. If you add one additional relation, or two IC relation or 2 equivalents, yeah, this is perhaps a better word, 2 equivalents. So, and then 3 equivalents, it would be generated by adding and removing additional, so cancellation of 2-3 pairs, meaning that topologically it means that I can add a sphere. So to my 0 cell, I can just add a sphere and then remove it with 3 handle. And so these 3 equivalents are on the level of the group presentation. It's the following thing. So I can just add one trivial word. So I have all the guys together with one relation, which just this is one trivial relation. And if I add to these 2 equivalents, this 3, so this additional moves, then I call it 3 equivalents. And now there is a 60-year-old conjecture by Andrew Curtis. Then, so if you have 2 presentations of a trivial group, which are 3 equivalent, then they are also 2 equivalent. So this is the ordinary AC conjecture, and generalized in this setting, generalized IC conjecture is that so if any 2 CW complexes are 3 equivalent, then they are 2 equivalent. And I know so this may sound completely boring, but if you can prove this conjecture, so even just for the trivial group, if you just can prove it for the group which looks like this, so this is a presentation with 2 generators and 2 relations, so it's a family. So this is a trivial group, but nobody knows whether it's Andrew Curtis trivial, whether it's trivial in the sense of 2 equivalents. if you can prove this, and you can prove the Riemann slice conjecture and generalize R conjecture. So there are many important topological things which just rely on this algebraic fact, whether you can reduce it modulus as subset of morph or not. And the last thing what I wanted to say is that actually there is a quotient of this 4-out by requiring that the braiding in 4-out is trivial, so just symmetric braiding. And the fourth braiding is trivial, and the Riemann element is 1. And what you obtain in this way, it's a category 2-out. And then I'll finish by drawing a diagram. Oops, here. I don't know where. Oh, can you see it here? Can you see it here? Okay, so I explained you that there is this 4HB, and which is equivalent to 4-alg. And that you have a boundary map from 4HB to 3-cop, and this is equivalent to 3-alg. And you have a quotient map from this 4-alg to the 3-alg. And now you have, by taking just pi 1 of this Handel body, you're coming to this relative presentation of the group. This is equivalent to this quotient 2-alg, which is another quotient of this 4-alg, where you set your braiding to be just flipped, and your Riemann element to be just the identity morphism. And we are claiming this presentation equivalent to this 2-alg, 3-cop equivalent to this 3-alg, and then to study the Andrew-Curtis conjecture, one need just to find interesting linear presentation of this 2-alg as a symmetric Kopf algebra object in symmetric monoidal algebra. Thank you so much.
Thank you very much. Very interesting. Are there any questions for Anna?